Welcome to G Fun Facts Online. Today, we are focusing on a singular machine that is currently being forged in the fires of iterative development. A machine that promises to shift our civilization from merely visiting other worlds to inhabiting them. We are talking about the Starship V3. The history of spaceflight is often told in chapters defined by the vehicles that carried us. The Mercury Redstone proved we could survive the vacuum. The Saturn V proved we could leave Earth's orbit. And the Space Shuttle proved we could return and reuse our craft. We are now witnessing the opening of a new chapter. At the center of this revolution stands the SpaceX Starship, specifically the third generation, or V3. While the early prototypes of Starship captured the world's attention with their fiery tests and dramatic belly flops, it is the V3 that represents the mature, operational architecture capable of delivering on humanity's oldest science fiction dream, a permanent city on the moon. This is not merely a larger rocket. It is a fundamental reimagining of space logistics, a cathedral of stainless steel and cryogenics designed to turn the lunar surface from a distant destination into a bustling industrial frontier. To truly understand the V3, we first need to look at the evolution of the species. The Starship program has been defined by a philosophy of hardware-rich development. This means building, flying, breaking, and fixing at a cadence unseen since the height of the Cold War. Starship V1 was the pathfinder. It proved that a stainless steel rocket could survive the rigors of hypersonic re-entry using that famous belly flop maneuver. It validated the fundamental aerodynamic control surfaces, the forward and aft flaps, and the concept of propulsive landing for a vehicle of this mass. Then came Starship V2, often referred to as the Block II vehicle. It refined these concepts, introduced significant weight savings, optimized the heat shield tile placement, and began the transition to more reliable Raptor 2 engines. However, V2 was still in many ways a prototype architecture. It had payload limitations and relied on a hot staging ring that was an add-on rather than an integrated feature. Enter the V3, the stretched titan. Starship V3 is the realization of the system's full potential. The most immediate difference you would notice standing next to it is the physical scale. While previous iterations stood around 120 meters fully stacked, the V3 architecture stretches the vehicle to approximately 150 meters in height. This elongation is not for vanity. It is pure utility. The upper stage, the ship itself, has been stretched by over 10 meters, allowing for a massive increase in propellant capacity. This is the critical unlock for deep space missions. The tyranny of the rocket equation dictates that for every kilogram of payload sent to the moon, you need exponential amounts of fuel. By stretching the tanks, SpaceX has increased the delta versus capabilities of the ship, allowing it to carry heavier payloads, up to 200 tons to low Earth orbit, in a fully reusable configuration, without needing to radically alter the diameter or the launch infrastructure. The Super Heavy booster has also grown, accommodating more propellant to loft the heavier upper stage. But size is only the most visible change. The true revolution lies under the skin, specifically in the propulsion. The soul of any rocket is its engine, and the Raptor 3 is perhaps the most advanced internal combustion machine ever built by human hands. It represents a complete deviation from traditional engine design philosophy, which often prioritizes redundancy and protection. The Raptor 3 prioritizes simplicity through integration. If you look at a Raptor 1 or even a Raptor 2 engine, you see a spaghetti of plumbing. There are fuel lines, sensor wires, hydraulic actuators, and helium purge lines wrapped around the powerhead. It looks like a complex industrial boiler. The Raptor 3, however, looks like a sci-fi prop. It is smooth, sleek, and almost entirely devoid of external piping. This is because SpaceX engineers have achieved a feat called integral cooling. Instead of running separate tubes for cooling and fuel flow on the outside of the engine, these channels are printed or cast directly into the walls of the engine block and nozzle itself. The structure of the engine is the plumbing. Perhaps the most radical change in V3 is the elimination of the engine heat shield. On previous rockets, the base of the vehicle, known as the dance floor, had to be protected from the searing heat of 33 engines firing at once, as well as the plasma of re-entry. This required heavy, fragile thermal blankets and physical shields. Raptor 3 deletes this requirement. The engine is robust enough and its regenerative cooling is efficient enough that it can survive the thermal environment of launch and re-entry naked. The engine itself acts as the heat shield. This saves tons of mass, and in rocketry, mass saved is payload gained. The performance metrics of Raptor 3 are staggering. It produces approximately 280 tons of force at sea level, with a roadmap to over 300. It operates at a chamber pressure consistently above 350 bar, higher than any operational engine in history. And crucially, it is significantly lighter than Raptor 2, giving it an unprecedented thrust-to-weight ratio. For the lunar mission, this efficiency is vital. The higher specific impulse of the Raptor vacuum engines, of which V3 carries 6, up from 3 on V1, means that less fuel is wasted during the long coast to the moon, reducing the number of refueling flights required in Earth orbit. Now, let's talk about what holds this beast together. While carbon fiber was the original choice for SpaceX's interplanetary ships back in the ITS era, the pivot to stainless steel has proven to be a masterstroke. Starship V3 utilizes a proprietary alloy often referred to as 30X, a cold-rolled stainless steel that evolves beyond standard 304L. The magic of this steel is its behavior at cryogenic temperatures. Most metals become brittle when exposed to superchilled liquid oxygen at -183 degrees Celsius. 30X steel, however, actually sees its tensile strength increase as it gets colder, without losing ductility. This allows the hull to be lighter than a comparable aluminum or carbon fiber structure would need to be to hold the same pressure. Constructing a 150-meter tower of steel requires welding technology that borders on art. Starship V3 is built using automated continuous laser welding robots. Unlike traditional friction stir welding, laser welding puts very little heat into the surrounding metal, minimizing warping and ensuring a seamless barrel. The result is a vehicle that is structurally uniform, behaving almost like a single extruded piece of metal rather than a patchwork of rings. This structural integrity is critical for the catch maneuver. The Super Heavy booster does not land on legs. It is caught in mid-air by the chopstick arms of the launch tower. The V3 booster has reinforced load points under the forward grid fins to absorb the shock of a 250-ton metal skyscraper being snatched out of the sky. While the standard Starship V3 is a jack-of-all-trades, designed for satellite deployment and Mars transport, the Moon requires a highly specialized variant, the Human Landing System, or HLS. The Moon has no atmosphere. This renders the standard Starship's most iconic features, the heat shield tiles and the aerodynamic flaps, useless dead weight. The HLS variant strips these away. It is a sleek, white cylinder, insulated to prevent propellant boil-off during the days-long transit in direct sunlight. Landing on the Moon is fundamentally different from landing on Earth. There is no air to brake against, so the entire descent must be propulsive. Furthermore, the lunar surface is not a concrete pad. It is regolith, ancient, jagged dust and rock that can shift and compress. Starship V3 HLS features a wide-stance landing leg system. Unlike the Falcon 9 legs, which fold up against the fuselage, the HLS legs are designed to be robust, self-leveling shock absorbers, capable of handling a slope of up to 15 degrees. They must support the immense mass of a fully loaded ship without sinking into the dust. Another unique challenge of the HLS is the elevator. The sheer size of Starship presents a problem. The crew cabin is nearly 30 meters or 100 feet off the ground. You cannot simply jump down. The HLS features a heavy-duty elevator mechanism, a porch that lowers astronauts and cargo from the airlock to the surface. This elevator is a critical single point of failure system, engineered with multiple redundant motors and cables to ensure no astronaut is ever stranded in the cabin or on the surface. The airlocks themselves are massive, designed to handle dust mitigation. Lunar dust is electrostatically charged and incredibly abrasive. The V3 HLS airlocks are expected to feature suit cleaning systems and potentially separate dirty and clean zones to prevent the regolith from contaminating the living quarters. Now, getting a vehicle as massive as Starship V3 to the lunar surface requires a change in how we think about propulsion. It is not about building a rocket big enough to go there in one shot. It is about in-orbit refilling. The campaign begins not with the lander, but with a Depot Starship. This modified V3 is launched into low Earth orbit to serve as a floating gas station. Once the depot is stable, a fleet of Starship V3 tankers launches. These ships carry nothing but fuel. They rendezvous with the depot, transferring liquid methane and liquid oxygen. Because V3 has larger tanks and higher payload capacity, fewer tanker flights are needed compared to the V2 architecture. Estimates suggest that 6 to 10 tanker flights could fully fuel a depot for a lunar mission. Finally, the HLS Starship launches. It meets the depot, tops off its tanks to 100%, and then performs the trans-lunar injection burn. The HLS enters a near rectilinear halo orbit around the Moon. Here, it waits for the crew, who arrive aboard NASA's Orion capsule. The crew transfers to Starship, which then acts as a massive shuttle to the surface. The descent to the Moon is a powered, retrograde burn. Starship V3 must kill thousands of miles per hour of velocity using its engines. As it nears the surface, it relies on the deep throttling capabilities of the Raptor 3 to touch down gently. Starship V3 is not just a transport. It is the first building block of the lunar city. Its payload capacity, over 100 tons to the lunar surface, changes the economics of base building entirely. Traditional lunar base concepts involve small, inflatable modules. SpaceX's vision is bolder. A landed Starship is a habitat. It has a pressurized volume of over 1,000 cubic meters, which is more than the entire International Space Station. The first few V3 HLS units may simply land and stay there, serving as the initial Moonbase Alpha. To build a self-growing city, you need heavy industry. You need excavators to dig regolith for radiation shielding, solar farms, and nuclear kilopower reactors. Starship V3's cargo bay is designed to deploy these massive payloads. Concepts include the PEZ dispenser for Moon, a modified door mechanism that slides heavy rovers out on rails, and internal gantry cranes capable of lowering 20-ton modules down the side of the ship. There is also the sky crane concept, where Starship hovers 50 meters off the ground and lowers cargo on winches to avoid dust impingement. Powering this base through the lunar night, which lasts 14 Earth days, is a major challenge. Batteries are heavy. Starship V3 enables the transport of small modular nuclear reactors, or massive vertical solar arrays that can catch the perpetual sunlight at the lunar South Pole peaks. The ship's own header tanks and power systems can provide initial survival power for the base until the main grid is online. The defining characteristic of the V3 era is cost. The Apollo program cost roughly $280 billion when adjusted for inflation. The SLS rocket costs over $2 billion per launch and is expendable. SpaceX is targeting a marginal launch cost for Starship of under $10 million. Even if the commercial price is higher, the massive payload capacity brings the cost per kilogram down to numbers that make industrialization viable. We are talking about potential costs of under $500 per kilogram to the lunar surface. This drastic reduction implies that we don't just send science experiments, we can send bulk materials. We can send steel, glass, water, and eventually hundreds of colonists. It moves the moon from the realm of exploration to logistics. Despite the optimism, the engineering challenges facing Starship V3 are immense. Keeping methane and oxygen liquid for weeks in deep space is difficult. The sun boils it off. V3 must master zero boil-off technology, using active cryocoolers and advanced insulation. If the fuel boils away before the return trip, the crew is stranded. Then there is the dust. Lunar dust is sharper than broken glass. It destroys seals, clogs bearings, and ruins lungs. A reusable lander that flies repeatedly between orbit and surface will accumulate dust in its engines and airlocks. Engineering dust-proof mechanisms for the V3 HLS is perhaps the greatest unsolved problem of the program. And of course, there is the refueling bottleneck. The entire architecture depends on the rapid cadence of tanker launches. If the launch tower jams, or if regulatory bodies delay licenses, the HLS sits in orbit with boiling fuel, waiting for a refill. The logistics chain is fragile. In conclusion, Starship V3 is more than a collection of tanks and engines. It is a declaration of intent. It signals the end of the flags and footprints era of lunar exploration and the beginning of the bricks and mortar era. By engineering a vehicle that is fully reusable, massively scalable, and brutally efficient, SpaceX is removing the greatest barrier to space colonization: the cost of the ticket. When the first Starship V3 touches down at the Shackleton crater, kicking up a silent plume of gray dust, it will not just be landing, it will be grounding a new branch of human civilization. The moon is no longer a destination to visit. With Starship V3, it is becoming a place to stay. Thanks for joining us on G Fun Facts Online.